everyone's ready. Joe, I think we're ready for you to start the meeting.
Okay, so let me just get the meeting started. Good morning, everybody. This is Joe Garfunkel, the CCL Houston chapter leader. And thank you so much for joining us either remotely on Zoom or in person. It's always good to see everybody. And I'm going to hand this over now to Dory to do the introduction for our guest speaker today.
Actually, Court's going to do it. Court's on. So Court's going to do
great.
the
Hey there. Good morning, and thanks everyone for attending our monthly meeting. We are very excited and very appreciating of Dr. Sylvia Dee, who's joining us for this. And she is an assistant professor in the Department of Earth and Environmental Planetary Science at Rice University. She has been at Rice since 2018. She received her bachelor's degree in civil and environmental engineering at Princeton University. She received her PhD in climate dynamics at the University of Southern California. And she completed postdoc fellowships at Brown University and UT Austin. Whenever she teaches at Rice, she teaches courses in environment and society, introduction to climate change science, paleoclimate, and climate physics and modeling. Outside of her duties at Rice University, Sylvia regularly leads environmental science programming for the Girl Scouts of the USA, work for which she was recently honored with the Global Leadership Award by the Girl Scouts of New England. She is a regular contributor to media coverage on climate change, including sources as NPR, AccuWeather, and the Houston Chronicle. Sylvia loves working with Rice undergrads to find solutions to environmental problems. Thank you again for joining us, Dr. Dee, and we look forward to your presentation.
And if I can just ask everybody, please go on mute so we don't have any interruptions during the presentation.
Thank
Dr.
you so
Dee,
much for
please feel free to present on your computer now.
Okay.
Sure.
Can you all hear me all right?
We can, yes.
Okay, perfect. Great, thanks for inviting me. I've been meaning to come and talk with your group for so long, and life gets so busy, but I'm really glad we're finally connecting. And I actually met with some of your colleagues from Braver Angels too on Zoom a couple of weeks ago, which was great. I'll do my best to try not to move around so much so the camera can follow me around. But I have about 30 minutes, maybe less, of stuff that I'll go through pretty quickly to allow most of our time for discussion. The messaging that I give whenever I give this talk is that climate change is simple, serious, and solvable. I like to start off with this animation from NASA. This is aerosols in the atmosphere. So the blue colors are sea salt, the white colors are smoke, and then this is dust coming off the Sahara. And this is, of course, the 2017 hurricane season. You might have just seen Harvey barreling into Houston with Irma, Jose, Maria shortly behind. So you can see all of these hurricanes from space. We can also see things like wildfires. So in the Pacific Northwest, you see all this smoke coming off of the continent here. So one of the things that I think is a real misnomer in the climate change world is that people think of this as a future problem, but really it's a past and present problem, right? Climate change is very much upon us now, and something we have to deal with now. So coming back to my key messages, if you don't remember anything else or think the rest of my talk is horribly boring, the science is simple, the impacts are serious, and the problem is solvable. I'm going to talk through each of these themes one at a time. Earth is a very unique planet. We are far enough from the sun to have liquid water, and we're also close enough to the sun for our water not to freeze all the time like it does on Mars. So we call this the habitable window. It's really a very small little section of the solar system. And so if you ever talk to someone who works on exoplanets, we look for other planets that are in these Goldilocks zones. And we're really motivated in climate science by the fact that our planet's very unique and we don't have a planet B. And we also don't have an experimental Earth, right? We don't have a perfect mini Earth that we can put in a test tube and heat up. And so We're really running an active experiment on our planet right now. And we know that our atmosphere has been in very delicate chemical balance for millions of years. So, for example, we can measure, as I'll show you, concentrations of carbon dioxide and methane going back millions of years to understand how our atmosphere has evolved. And one of the things we know about Earth's atmosphere is that it keeps us warmer than we would be otherwise. So we have our greenhouse effect, and our atmosphere contains gases like CO2 and methane that keeps the Earth relatively warm. And our temperature is critical for life. So I mentioned that our liquid water allows for life on Earth. This is because we have an atmosphere. Without an atmosphere, the average temperature of our planet would be about -16 degrees Celsius. So we would, in fact, be a frozen planet. And the way this works is we get shortwave radiation from the sun that heats up the surface of the Earth. We emit infrared or long wave radiation back to space that cools us back off. So this is just the conservation of energy. Energy in equals energy out. We get sunlight, we emit infrared radiation back to space, and our atmosphere keeps us a little bit warmer than we would be by re-radiating some of this long wave radiation back to the surface. Right now, of course, we're adding additional carbon dioxide, methane, and H2O to the atmosphere, and that's actually increasing the thickness of our atmospheric blanket. So I wanted to quickly talk about how this works because it's very important. So how does this effect of adding more CO2 to the atmosphere actually happen? So the way I explain this to my Girl Scouts is that CO2 molecules and methane molecules in the atmosphere, they're on a long wave radiation diet. They like to absorb our outgoing long wave radiation that's trying to escape to space. And when they absorb that radiation, they start to dance. So I have them do the CO2 dance and the methane dance. We do all the dances. But just like the Girl Scouts, when they start to dance, they get hot. So these molecules are vibrating and spinning and stretching and bending in the atmosphere, and they convert radiation to heat locally. So essentially, as they're absorbing radiant energy that's trying to escape Earth's atmosphere, they re-radiate it as heat locally. And so if I start off as a piece of radiation at the surface of the Earth, I'm trying to get out back to space to cool Earth off, I'm intercepted by greenhouse gas molecules, right? They're absorbing that long wave radiation and they're re-sending it back to the surface. So in a natural greenhouse effect, again, we have solar radiation heating Earth's surface. Some of that heat escapes to space. Some of it is trapped by the greenhouse gases in our atmosphere and re-radiated back to the surface, which keeps Earth about 30 degrees hotter than it would be under no atmospheric conditions. Right now, what we have is a human enhanced greenhouse effect. So we're just amplifying the magnitude of our natural greenhouse effect by adding increased levels of CO2, methane, and N2O. So we're essentially increasing the thickness of our atmospheric blanket such that Earth is warming at a rapid rate. Some of the analogies I give to my students are we have a taller goalie, blocking radiation from escaping to space like a soccer goalie, or we have more sponges sitting up in the atmosphere, just absorbing that extra radiant heat energy. So that's really all there is to the science of climate change, right? This is the greenhouse effect. CO2 absorbs outgoing infrared radiation from our surface. If we increase CO2 concentrations, we increase the amount of heat the atmosphere can trap. There's obviously a lot of detail that goes into things like optical depth and opacity and how CO2 absorbs radiation and at what atmospheric heights. These are the kinds of details I teach my graduate students, but for the purposes of public knowledge, this is the greenhouse effect. Everybody on mute?
Dory, could you put people on mute, please?
Okay.
I've lost my access to the co-host, so I can't mute people.
Okay, well, that's fine.
Okay.
I might be able to do it.
Recording in progress.
Everybody needs to mute. Thank you. Okay. Okay. Sure. Okay, great. Yeah, so that's really all there is to it. I need to be able to use the computer.
Yeah.
So if you can do it on that one, it'll work. Yeah, okay, so moving on. So right now we're profoundly altering Earth's climate system through these two effects. We're using the atmosphere as a dumping ground for excess CO2. So this is the total amount of carbon emissions just from 1959 to 2018. So, you know, we're hovering around 40 billion tons of CO2 emissions per year. And we're profoundly altering Earth's climate system. So the way that we think about these numbers in climate science is we use these units of watts per meter squared. So the total radiation retained by the atmosphere due to human activities, right now, the instantaneous additional radiation in the atmosphere is 3 watts. So you all have changed a light bulb before, yes?
Mhm.
So, you know, you've maybe put in a 60-watt light bulb or a 100-watt light bulb. 3 probably doesn't sound very much like 3 watts, right? This is just power per space, meter squared. So, you know, if I'm standing in a meter squared here and I have an additional 3 watts, that might not sound like a lot. But, you know, what if I take that and multiply it by the state of Texas in meters squared, or if I multiply it by, you know, the entire surface area of the Earth? If you multiply it by the entire surface area of the Earth, it's 4 nuclear explosions per second. Actually, when I gave the talk that you were at, Richard, Tom, one of the people in the chat said, that can't be right. And then someone did a back of the envelope calculation. They're like, oh, she's right. So I promise I'm not making this up. Yeah, so the human influence on the climate system is really unequivocal. We're smashing the atmosphere with like a truly gigantic extra amount of radiation. So how do we figure out what's happening in response to this additional heat energy to the climate system? We use 3 different tools. The first is weather station measurements and satellites. So these are our real data that we use to track climate change from space and also on the ground. We also use past climate data. So this is part of what I do in my lab. We use things like trees or corals or ice cores to go back thousands of years in time to see how Earth's climate has evolved. And then we also use climate models, which I'll talk about a little bit later. So what do these different tools tell us about how Earth is changing now? This is weather station data just for the United States. So this is departures or differences in temperature from the long-term average from 1971 to 2000. So the blue bars mean it's colder than usual, and the red bars here just mean it's hotter than usual. So, you know, we can make these graphs for every place in the United States. Maybe some of you have seen this tool. It's Ed Hawkins. Show your stripes. If you Google that, you can make these graphs for any city in the United States or anywhere in the world, or any country. So we can see that at least in the United States, temperatures are increasing much more rapidly in the last 3 decades or so. So we know Earth is warming just from looking at weather station data. If we extract this out to the globe, these are temperature anomalies, or again, departures from the long-term average from 1850 to 2017. Sorry, this is hard to see, but this is the 1850s here up through the 2010s. So again, just looking at the red versus the blue colors, we can see that there's been a big acceleration of global warming in the last 3 or 4 decades. And we know that the oceans are heating up. We know ice is disappearing, and we know sea level is rising. So we have satellite observations of ice cover. We have in situ and also satellite observations of ocean warming, and we have coastal arrays that are measuring sea level change in real time, as well as satellite data. This is satellite measurement of ocean heat content from 1960 to 2008 at different depths in the ocean. So over the total depth here in purple, again, we see that there's some variation, but on the whole, the total amount of heat stored in the ocean is going up. And again, this is not models, this is observations of weather and climate. These are satellite observations of Arctic sea ice thickness that my colleague Zach Wade made. So you can see that over time, Arctic sea ice has diminished in terms of its extent, but also its thickness, which again, we can see with essentially gravity-based satellite observations from space. So when people say, oh, how do we know what's happening to Earth? And I know this is not a surprise to any people in this group. We have multiple independent measurements showing that the land surfaces, the oceans, and the atmosphere are warming. The IPCC, the UN Intergovernmental Panel on Climate Change, has been delivering this message to policymakers since the 1970s, essentially. We've been saying that warming is unequivocal, the human influence is clear, and that emissions reductions will be required for many, many decades now, based on this evidence that comes, again, just from observations that Earth is heating up. I think it's very important to talk a little bit about where we've been and where we're going, because often you hear the case made that, oh, Earth's climate changes naturally, and we've gone through hotter and colder periods all the time. So that's true, right? 18,000 years ago, we were in an ice age. We've had ice ages every 100,000 years or so, forced by orbital forcing called Milankovitch cycles. And that's a reasonable question to explore. Well, how do we know that the rate of warming is different compared to periods in the past? Isn't this part of a natural cycle? How do we know that the warming and the carbon dioxide rise is unprecedented in the geologic record? And, people in my department, and myself included, we can answer this by looking into the planet's past. I'm going to turn my camera off. Just realized I'm kind of strangely, well, it's fine. We can look at data from things like trees, corals, ice cores, lake and marine sediments. So I have many colleagues who go out on NSF, basically ocean vessels, and retrieve marine cores from the ocean, and we can reconstruct climate going millions of years back in time. So if we look at Earth's history in terms of temperature, so just to go through this graph slowly, this is 100 million years ago here on the left side of the x-axis, moving forward to today. So on the colored picture here, this graph here is global mean temperature compared to today, okay? This is CO2 in gray. These are our best reconstructions of CO2. Each one of these little maps is tied to a different period. So this is the mid-Cretaceous, about 90 million years ago, the early Eocene, the Pliocene, it's about 3 million years ago. Here's our last glacial period. You can see it's blue, that means it's a little colder. We can see there are ice sheets in Antarctica and in the Northern Hemisphere in the more recent geologic past. And then these maps here show the temperatures we're headed towards in a low emissions future, so low carbon emissions, middle carbon emissions, and a high emissions future. So again, we're looking at something between 500 parts per million volume CO2 or 2000. So we can stare at this and say, yeah, okay, it was colder in the past, it was hotter in the past. The future gives us somewhere maybe in here. So where are we in geologic context? One critical feature of this graph that people often overlook when they make the argument climate has always changed naturally is that Homo sapiens evolved about 1 million years ago. And 1 million years ago, Earth was actually in a glaciated cold ice age period, right? We actually did just fine as a species handling ice ages, right? And if we look at the temperatures we're heading towards, right, with substantial emissions reduction, that's about 2 degrees Celsius of warming on average. In a high emissions future, it would be closer to 5 degrees Celsius. And if we look at the last time Earth was that hot, 2 degrees puts us at about 10 million years ago. Okay, so 10 million years ago right here. No emissions control puts us at 5. That's getting closer to 65, 60 million years ago in the Eocene. So, I always ask the question to my audiences, what animals were dominating Earth 65 million years ago? Dinosaurs, yeah, that's right. You got it. So, it is accurate to say that Earth has had different time periods with colder and hotter weather, but our species has not necessarily evolved to cope with those temperatures. So climate has always undergone major changes naturally in the past. As much as I love Jurassic Park, this is not necessarily a climate that I want to live in. This is a climate that supported massive full-blooded reptiles, right? So, that argument has flaws. And then the other thing to think about with the argument that, climate has always changed naturally is the rate, right? If we look back in geologic history, the time over which Earth has cooled down or heat up is over millions and millions of years, not decades. So the rate and the magnitude of temperature change that we're seeing now is really unprecedented in the geologic past. So now I'm just going to move on to the impacts, and I'll go through this quickly because I think we are bombarded with this in the news every day. You know, here in Texas, if we look at future impacts in terms of the number of days over 100 degrees Fahrenheit, this is from the National Climate Assessment. We're expecting, I hate to break to you, but between a month and 2 months of additional days over 100 degrees by mid to late 21st century, depending on carbon emission scenario. So even in a lower carbon emission scenario, another month of days over 100 degrees doesn't sound good to me. We know that these extreme heat days are going to have things like impacts on fire risk and also agricultural and water stressors. Our tropical cyclones, our hurricanes are becoming more powerful. This is Hurricane Delta, which just barely missed us a couple of years ago, and unfortunately dramatically impacted our colleagues in Louisiana. Basically, as you heat up the ocean surface, hurricanes can gather more fuel and they can become windier and rainier. We know that this is what's happening now. This is a picture from nearby. Probably you've all driven through this intersection, and this is of course from Hurricane Harvey. I always make the joke that I don't really know why this guy's smiling, as fun as this kayaking looks, because Harvey cost us $125 billion. But all joking aside, these flooding events are causing tens of deaths and more in other countries. If you look at the floods that happened in Kentucky this past fall, there were many deaths associated with these events. If you look at the flooding that happened in Pakistan, it was tens of thousands of deaths. So we're of course affected by this all the time. Since I started at Rice, I've had four or five students who've had to leave in the middle of the semester because their homes burned down. So, we think of this as happening to other people. It's really not. It's happening all around us. So, in terms of human impacts and how our system is changing and what's happening, we see biodiversity loss. I don't really have time to get into all of that today, but we're losing access to things like ecosystem goods and services because of climate change. We see an increase in the risks of meteorological disasters, drought, floods, heat waves, extreme weather, sea level, freshwater availability, and I'll talk a little bit about public health and conflict as well. There's really the propagation of the impacts of climate change really can't be understated. And this is costing us a lot of money. So this is the total number of billion-dollar weather and climate-related disasters from 1980 to 2022. Texas is unfortunately winning in terms of how much we are paying for climate and weather-related natural disasters. Louisiana and Florida are usually pretty close behind us in a given year. But we are, we the taxpayers are paying an incredible amount of money for these climate damages. So given these stark impacts, one of the things I and my colleagues very much want to know is how much worse are these disasters going to become? Not just because we're, interested from a scientific perspective, we are, but we also need to be able to properly characterize risk so that we can make solutions and, work with policymakers to figure out what we need to do. But as I mentioned before, answering this question is not trivial because we don't have a perfect mini Earth that we can put in a test tube. Our colleagues in biology and chemistry, right, they can do controlled experiments in the lab. We cannot. The Earth is a very complicated system. So what do? We use climate models. So we build computational models of the ocean and the atmosphere. We essentially just solve physics equations, conservation of heat, conservation of momentum. At every grid cell, we dice up the atmosphere and the ocean into a lot of little grid boxes, and we run them forward in time. And to run a simulation on a climate model for the 21st century from 2000 to 2100 takes, a long time. It's about 2 months of computing power. So there's a lot of computing resources devoted to these simulations. Many of them are run through NASA or NSF. These are NASA's climate models showing temperature and drought projections for the 21st century. And we run these models into the future, and we trust that they're working properly because we ground truth them against the 20th century. We check that they're operating properly. We do, thousands and thousands of tests to make sure that we trust their output. And what we're finding increasingly is that climate model simulations are actually conservative compared to the rate at which changes are happening now. And again, we unfortunately see that temperature increases and things like loss of freshwater availability are things that are going to become big problems in the future. Maybe some of you have been to Las Vegas, right? When I talk about water issues, here in Texas, we have very eclectic water issues ranging from burst water mains to flooding, but in other areas, especially in the U.S. Southwest, this is Lake Mead, which is the reservoir that supplies water to many areas around Nevada and the city of Las Vegas. This is where the water used to be. It's dropped by over 100 feet. And, this is an engineering problem. The water has dropped below the pipes that pump the water into the city. So now they have to build all new pipes. So again, when we talk about this getting expensive, it's not just that the water levels are dropping, but it's causing major infrastructure challenges. One of the things we work on in my lab that my students and postdocs are working on is how global warming is affecting extreme precipitation and flooding in the US. And one of the regions we focus on is the US Southeast and the Mississippi River Basin. So this is the lower Mississippi Delta on a normal day from satellite data Landsat. This is the flood that happened in spring 2011. And we've actually seen a pretty big uptick in major floods on the Mississippi. The floods are lasting longer. So they're not just a couple days, it's a whole month of elevated water levels. So we're trying to track how these big river systems in the United States are changing over time. The aerial flooding affects agriculture, it affects barge traffic, it affects human life, it affects infrastructure. So really we need to have better constraints on how these floods are changing as we warm up the atmosphere. You might have seen the opposite news this past fall. The Mississippi hit a 10-year low and it interrupted barge traffic in the other direction. So the river was so low that there was a big economic impact. And we know that this is probably driven by the big La Nina that's been happening in the tropical Pacific. But in general, we're trying to better predict out to about a year ahead of time what these big rivers are doing as you compound climate change with what's happening naturally. So these are the kinds of topics that we're trying to do better with so that we can make plans for the future. We actually go and do physical model experiments where we take water and pump it through a warehouse-sized model of the Mississippi River. So, in my very kind introduction, I actually had a past life as a civil engineer. So if you ever go to Baton Rouge, you should go to the River Center that LSU has. It's right on the river. It's a beautiful museum about the Mississippi and its flood control infrastructure, but they have this whole warehouse-sized scaled model of the Delta. And they literally pump water through it and have all these cameras at the top and along this to see how water flows through the model. So we take our climate model experiments and we get some estimate of how flooding might change, and then we run it through an actual physical model of the system. So these are the kinds of tools we have to try to estimate risk of future hazards. So now I'm going to talk a little bit about the human side, and then we can save the rest of our time for discussion. As I'm sure all of you that are working with this group know, the politicization of scientific fact is a major challenge in climate science. And one of the big, I think, sad, travesties I would really call it, is that climate and environmental regulation really wasn't politically divided until the early 2000s, after the hockey stick curve was published. And there were some interesting political reasons for that. But, if you look back at the Bush 1 administration, or even the Reagan administration, environmental regulation was something that was widely adopted, right? We had the Clean Air, Clean Water Act. These things were not politically divisive. Cap and trade policies for sulfur and acid rain were enacted by the Reagan administration, right? These are this politicization of climate change is a recent phenomenon, and it's dangerous. And it's dangerous because of the public health impacts of climate change. So I'm sure you saw headlines like this during the Trump administration. There were rollbacks of regulations on everything from air pollution to health and safety to water pollution. And, you know, I hope you all saw the news that the Texas state legislature has put forward a number of bills to basically subsidize natural gas and cap how much renewable energy production can happen in Texas. I actually think this group, and I've been working hard to make calls against this bill, because this would be a disaster really for environmental progress. And it's being attacked as a way to basically benefit the natural gas companies and even big electricity utilities like NRG and other ones that own a lot of wind power are saying this is a terrible idea, right? Texas is the leader in wind power for the entire United States. Why would we stop? Why don't we just keep going? They're trying to basically bar that from happening. And this politicization of how we make our electricity in a changing climate is really moving us backwards. And why do I say this is dangerous? We as a scientific community have tried to do a better job incorporating environmental justice into our messaging, and this is really critical because, of course, climate and environmental change is a race issue, it's a gender issue, a class issue, and it's a health issue. So, you know, when I teach my introductory classes, I really try to make sure that my students understand, right? These are the headlines that we have all the time now, right? Environmental factors like pollution cause 1/4 of deaths worldwide, right? World Health Organization. These headlines are depressing, but they are a big wake-up call about how climate change and pollution and human health are intricately linked. So if we can't, you know, stomach talking about these things side by side, right? We've known that environmental pollution causes health problems for many, many decades. I don't know why this isn't, you know, part of the discussion surrounding environmental regulation. I think it is, but it needs to be, we need to be ringing the alarm bell more loudly. The other thing that we know from research is that historically, if you look at outbreaks of conflict and civil violence, it's tied to temperature and water scarcity. And you start to see headlines like this, even in the United States, 40 million people under heat alert, crime rates rising, right? So these are the realities that we're gonna have to deal with. You know, I also have seen evidence from the medical community recently that air pollution is linked to adverse mental health effects. So there's impacts from climate and bad air pollution that we don't even understand yet that are starting to happen now. We have been doing some work on this at Rice. So this is a fantastic team of all undergraduate students that has been doing things like reaching out to athletic staff across Texas to ask them, do you know how hot it's going to get? Do you know that we're going to have, you know, 2 months of additional days over 100 degrees? And then we work with epidemiologists who study basically extreme heat impacts on human health, things like exertional heat illness and heat stroke. You know, because this is as dark as all this can get, what's the critical thing we need to do? We need to talk to these coaches to make sure, do you understand what heat stroke looks like in young athletes? Are you aware of how bad this is going to get in the next 10 years? And what's your plan? Do they have access to climate controlled facilities, right? Are they willing to switch the season in which football is played to make sure that students aren't getting sick, right? These are the real questions we need to be thinking about. And, you know, to bring you back out here, I'm going to bring you all the way down and then bring it all the way back up here. I know that this is incredibly overwhelming. I know we all think about this. We lose sleep about climate change and human health. So this can be very muting.
Dory, if you can mute Dan Burns, please.
I'll do it. Let's see. Okay. Yeah, so, you know, my students have emotional exhaustion and overwhelm about all of these topics, and they've grown up in this culture where it's all very doom and gloom. But I really want to challenge that. And I do every time I give lectures, right? Marie Curie, famous Marie Curie, tells us we cannot fear these problems. We need to understand them very, very well so that we can fix them. And I really, truly believe that, right? We can't be afraid of these problems. We really have to dive right in and have a lot of conviction as we try to solve this. This is a big problem, but we as a species have solved pretty big problems in the past, right? We just made a vaccine for a deadly disease in a year. Imagine what we could do about climate change if we took all the same urgency and brain power and devoted it to this problem. I mean, I don't have any doubts that somebody's going to invent carbon air capture in the next 10 years and solve this. I mean, it's going to happen. They're going to make billions of dollars. This is a gigantic economic opportunity. We have the power to control our own environment and our future. You know, I'm a climate scientist. My job is to report on how things are changing and how they are likely to change in the future. But I'm incredibly uplifted by the innovation of my students and the innovations of all the young people that I talk to, and also the work by groups like CCL, right? Which is the last piece, which is the problem that's solvable. I mean, even just thinking from a first principles perspective, you know, like CCL, these are things that we're all working on. Everybody needs clean air. Everybody needs clean water. Most people don't want more natural disasters, although we do care about studying hurricanes. You know, most people care about conservation of wildlife and landscapes. These shouldn't be controversial topics. Every single conversation I have, you know, with policymakers and other people at Rice and everything, Texas state legislature, when they'll talk to me, is about environmental solutions. We don't have any more time to be talking about whether or not climate change is happening. Leave those people behind, right? Every single conversation we have, we should be demanding solutions-oriented dialogue from our elected leaders. And things like this rollback or capping of renewable power, right? That's ridiculous, right? Everybody should be moving the needle forward to solve this problem, not backwards. And this, again, there's an easy way to frame this around economic incentives, right? More solar energy reaches Earth in 1 hour than we use in an entire year as a global society. So there's incredible potential to use free wind and free solar. Of course, you all know we have to spread this information. People have to be educated. They have to vote. And at the national level, at least, things are getting a lot better, right? There are climate bills. There's these big infrastructure bills, the Inflation Reduction Act. At the national scale, I can tell you, at least from my perspective, you know, in the science world, there's an incredible amount of funding coming down through the Department of Energy, the Department of Defense, NSF, NOAA, NASA, devoted to not as much figuring out the climate science of what's happening, because we kind of know at this point what's going on and where things are going to get worse. All of the funding is getting poured into solutions, right? Solar panel efficiency, reducing carbon emissions from absolutely every sector of society, climate adaptation, resilience, coastal resilience, flood infrastructure. That's where the money is getting poured into studying those kinds of solutions. I also tell my students, and if you work with young people or you talk to people who are trying to figure out their careers, you know, this is an all hands on deck problem. You all know this. There's so many jobs in this space that, you know, young people don't know about. They don't know that they can work in coastal hazards. They don't know that they can go work as an environmental lawyer. You know, whether they want to work in human health. I talk to a lot of pre-med students at Rice. You know, they've never thought about, oh, hey, vector-borne diseases are changing in climate change, and right, we see changes in malaria and Zika and their distribution because of changes in the hydrological cycle, right? I just showed you a whole lot of human health alignment with air quality. So, you know, these types of jobs and helping young people understand there's so many ways you can help work on this problem. Communication, right? Outside of science, these are important jobs.
I love the music.
Yes, so the music one, I thank you for stopping me on that. I have a student who took my class a couple of years ago, And he wrote a piece about hurricanes. It was beautiful. He composed an original piece about hurricane intensification and the importance of using art to communicate science is really, really important. And psychology, you know, I have psychology majors that take my course and we get to the 1 week that I teach on science denial, you know, right? This is important. People ask me, oh, well, why are people denying climate change? I don't know. You need to ask a psychologist, right? I can't answer that question. I don't have any training in social science. This is where we need everybody. We need everybody at the table. So this is a picture I show my Girl Scouts. You know, there's all these really wonderful jobs out there where young people can come together and all of us can volunteer our time to solving environmental problems. And I think this is the way forward, is helping people understand no matter what their interest or their skill set, they can contribute to the solution. So that's all I have. Thanks for listening. And I hope if you want any of this material, I'm happy to send you my slides. I have other stuff, like all of this is on the internet. So please just let me know and I'll email everything I have to you, because, you know, I just borrowed all these materials from my colleagues too and put them on pretty pictures.
And this has been recorded so you can share this with others.
Yeah. Yeah, I'm very, very happy to connect with your group. And I'm really, really grateful for all the work that CCL does and everywhere I've ever lived, but especially here in Texas. So yeah,
thank you, Dr. Dee. Thank you. If you wouldn't mind, stop sharing and so we can see all the faces. And I think we probably have a lot of questions right now.
Yeah, sure.
Perfect. So yeah, please, if anyone has questions, just go ahead and shout them out or put them in the chat if you'd prefer to do that.
And John,
Hands raised too.
Okay, Larry Howe, why don't you go first?
Hi, Dr. Dee, great presentation again. I think we connected back when you did a presentation for Tom Ream and the American Chemical Society back a couple of years ago. So I really appreciate your communication style and outreach. I had a question. You mentioned earlier that you'd done some work with Braver Angels. And I'm really interested in that because I've tried to do some stuff here in North Texas. And, you know, their goal is depolarization and trying to figure out how to people to hear both sides. But the challenge here on this issue is there's really not two sides on the science. And so they kind of, how do they, you know, they're trying to figure out how to do that. So have you had some success working with them to say the issue is not to depolarize the science, but, or the science is really, you know, doesn't have two sides. It's really the, you know, how you address the problem. Be interested in.
Yeah, so I think it's actually critical to make sure people understand there are not two sides here, especially on the science side, right? This is settled science. It's been settled for many, many decades. We've known CO2 causes global warming since the 1890s. And so I actually, when I do work with, you know, I guess groups across the aisle, so to speak, I'm very, very firm in making sure that there's no question on the science side. But then I do say, you know, our decisions about what we do about it, right? That's where I can understand how maybe people would have different views. But yeah, with the Braver Angels group, I think, you know, I talked to them because I wrote an op-ed about working with a Republican women's organization called Clear Skies that was very deeply concerned about climate change and human health and environmental pollution. And it actually had come from them, right? It was actually another group that has started feeling freaked out about how their party is aligning with sort of science denial, and that's not, they see that as not productive. They want to go back to, you know, depolarizing science. And so I've helped them come up with materials to help people understand the basics of climate change science, but also, you know, help people understand that the solutions also, right, the solutions also shouldn't be political, because again, like creating consensus about innovation and making money for the state of Texas, I just fail to see. You know, it just seems like there's a lot of preying on people's emotions, and the only advice I can give on talking to the quote unquote other side is you have to stick to the facts, right? I basically did a workshop with them on how to convey climate change facts to a skeptical audience. And, there's a lot of different strategies. And I've fallen into many traps many times where someone has, barreled into me and said, oh, well, volcanoes emit more CO2 than humans do. And there's a right and a wrong way to answer questions like that, and to be respectful and listen. But then also you have, like, the biggest thing is you have to correct erroneous statements, right?
Do you find that, so with Courtney DeBauer with Clear Skies, Texas, is there anybody in particular that you worked with Braver Angels that I could follow up with later to kind of continue the conversation?
Yeah, Beth, I forget her last name, but they were all over the US. They weren't here in Texas.
Okay.
They were a group that was meeting, but I'll send you their email address.
Okay, yeah, or if Joe, if you can capture that and send it out in your meeting notes, that'd be great.
Sylvia, maybe after the meeting, when you have a chance, you could email that info to us.
No problem.
Thank
Was
you
that
so much.
probably Beth Marlowe from CCL
Yeah.
Action Team? Okay, all right, great, thanks, appreciate it.
Thank you, Larry. Let's go to Larry Kramer, and then after Larry, we'll go to Jim Tucker and then Roger Ingersoll. Larry?
Great talk. I really appreciate it. And also thank you for sharing your slides, because I was in the Tom Ream group and I talked on cost, putting a price on carbon. And so you shared your slides, and I use it to teach the difference between big scale climate models and inroads, because several of us are inroads ambassadors that give talks on inroads. How many cells do you typically run in one of these massive climate models?
Yeah, so there's different kinds. The ones I use are at a 2-degree latitude longitude grid. So they're about 96 by 144 grid cells for the atmosphere. We also have 1-degree gridded climate models. So 1 degree of latitude is about 100 kilometers. But then there's also regional climate models that are run at 10-kilometer resolution. For weather forecasting, we use 30-kilometer or down to 1 kilometer. So depending on what scientific question you're trying to address, you can run the model at higher spatial resolution depending on what your goal is. So because I look at large scale weather and climate patterns, I tended to use 1 degree latitude longitude climate model simulations. But if we're running a simulation going back millions of years, we bump it up to 3 degrees because of the time requirement, right? The finer you go, the more computational power you need.
So it's tens of thousands of cells.
Yeah.
Okay.
Yeah.
Thank you.
Thank you, Larry. Let's go to Jim Tucker.
Yeah, thanks for a very clearly illustrated talk, and brings in a lot of directions. A couple of things. First, there's been a lot of discussion lately about use of virgin plant oils for essentially directed towards motor fuel. That seems to me to be no better than fuel ethanol, where the arithmetic doesn't work, because we're taking soil carbon and turning it into carbohydrates and then turning it into fuel. And it brings up another agricultural practice. The apparent excessive use of urea for an agricultural amendment, and the seeming excitement from hydrogen advocates for using that to make ammonia for combustion fuel, particularly for marine, which sounds like that's going to blow up on us, because we've been trying to get nitrogen compounds out of tailpipes for 40 or 50 years. Any reflections on some of these coming things that we need to think full cycle on? Thank you.
Yeah, so just based on your question, you know a lot more about biofuels than I do. But I can tell you that yeah, life cycle analysis and trying to understand whether or not the good outweighs the bad with some of these environmental solutions is really important. You know, I'm not an expert on biofuels. Professor Dan Cohan, who's my colleague in civil engineering at Rice, would be able to answer your question a lot better than I can, but I do know that, you know, there are big trade-offs with biofuels, with subsidies for crops, like you mentioned, soil carbon storage. There's also issues with water use and irrigation needed for biofuels. So, you know, I think they ultimately probably were born out of the fact that we're over subsidizing corn in the United States through kind of backwards farm bills. But at the end of the day, all the issues you pointed out with biofuels are problems, and we should be looking for environmental solutions where the good very clearly outweighs the negatives. I mean, this is the same thing that happened with natural gas. Everyone said, oh, it's a lower CO2 emission from burning natural gas, how great, but then the fracking contaminates water and releases methane. So if there's not a net benefit, why would we, yeah. Anyway, so I can't answer your question.
Joe, there's a question here. Richard has
I'd
a
like
question.
to comment on.
Excuse me 1 minute though. Roger was next, and then we'll take the question in the room, if that's okay.
Yeah, but I had a part of an answer for that previous question
Go ahead.
about carbon coming out of the soil. It doesn't really need to come out of the soil, but agriculture these days is trying to put more carbon in. That carbon's coming out of the atmosphere, and we need more of that. So be careful about how much you think carbon's coming out of the soil. It is still probably net coming out of the soil, but that's in the process of being reversed with what they call regenerative ag practices, and that's happening very fast. So comes out of the atmosphere where we want it to come out.
All right, thank you.
Almost not quite as good as the Brazilian rainforest, but corn's pretty darn good at taking it out of the atmosphere.
Okay, Roger? And then after Roger, I see, were there any more questions in the room after Roger goes?
Not yet.
Okay, and I do see a question in the chat. We'll do that one after Roger then.
All right, Dr. Dee, fantastic presentation. Thank you very much. My question is on paleoclimate, because that's whenever I do get into that a little bit about taking temperatures and CO2 content back tens of thousands or a million years. Like, there's a lot of skepticism. I'd just like to hear how you explain, you know, how you get that data from cores, whether they're ice or soil. If there's like a thumbnail description, that would be helpful.
Yeah, so I can send you the very, very large presentation. I show my students with videos of my colleagues who drill ice on the Antarctic continent and who collect cave records and marine records. And I have beautiful photos from people collecting samples in the field that might be useful to you. Yeah, you know, there's uncertainties in all of our data when we collect ice cores. You know, each of the types of paleoclimate data we use has their own array of uncertainties. But CO2 and greenhouse gas concentrations come from ice, and ice is something we know very, very well. The uncertainties on ice core reconstructions are extremely small. Why? Because we have ice cores from both Greenland and Antarctica that show the same exact signals, and they're highly replicated. And so we can show there's alignment in time and across space that show the same variations in CO2, methane, and temperature. And that's why ice cores have been so critical in paleoclimate. And, you know, at this point, we can go back 3 million years with ice. We can't go back further than that. Going back further in time, you know, when I show hundreds of millions of years, there's where we're using marine sediments. And again, we have confidence in those records because we drill cores not from one place, but from 400, right? We have 400 cores. We line them up in time. We make sure they show us the same signals, and we make sure that we understand all of the uncertainties in those signals. So for example, on continental shelves, sometimes you can miss, I don't know, 400 million years because it stopped raining sediment there. And if you weren't looking at 60 other cores from an Atlantic transect, you'd think, oh, this is the right data. But we catch those problems because we're replicating and making sure that the time horizons all line up with other sites. And so, there are large uncertainties in terms of like, how do you tie chemical compositions of shells back to global temperature? But again, we've been studying this since the 1940s, and we have pretty strong evidence when we link ocean records to ice cores, to cave deposits, to trees, and they all show us the same thing. Then we can generate confidence that our interpretations of that data is correct. And so we don't just use one record and one core and say, oh, this is what temperature was 50 million years ago, right? We get it from multiple data sources and we replicate it. And then we, tear each other apart in peer review for 30 years, arguing about whether or not our own interpretations are correct. So, it's not like the scientific community is not, especially in paleoclimate, it gets heated over whether or not these records are telling us what we think they are. So trust me that some of the stuff I showed you today is like well agreed upon, and some of the paleoclimate stuff people fight about. But the main messages I showed you are things that have been agreed upon, right, for a while now. So I don't know. I hope that answers your question, but I'm happy to send you materials, because I think it is important that people understand where we get these records from. It's really expensive to send an icebreaker down to Antarctica and retrieve all these cores, but we've done it for the last 50 years because they're such valuable records and they're so high fidelity, really.
That's great. Thank you.
Joe, are you frozen?
What?
Larry, you want to go while Joe is frozen? Do you have a question, Larry?
Yeah, I was trying to write down the reference you gave on one of your graphs. It was Ed somebody, and I didn't catch the last name.
Which graph?
It was one of the first ones you showed, and you said we could contact Ed somebody.
Oh, Hawkins. So if you just Google Sugar Stripes, the last name is Hawkins, Hawkins. I'll write it in the chat.
Okay, thank you.
I'm back now. I lost my connection temporarily. There was a question in the chat by Jenny. Would you like to read out your question?
Go ahead, Joe, and read it for her.
This is the question from Jenny. She says, I have a question. I work for United Airlines, and they have launched a program to utilize sustainable aviation fuel, which is called SAF. That's the abbreviation for it. Is that just another biofuel, or is the company greenwashing?
Yeah, so thanks for bringing the term greenwashing to the floor. I've seen those ads as well. I fly United myself pretty frequently. And I'm not sure if it's a biofuel or a synthetic fuel that they've proposed. I don't have enough information about that program, but I don't know if somebody else knows a lot about it, but I can look into it. I think if you work for them, you should ask questions, ask them questions. Okay, like what is this compound really? Ask questions about the life cycle analysis of how it's produced and how it's going to be disposed of, and what is the electricity demand of the production of the fuel, what's the carbon emissions from the production of the fuel versus how clean it burns, because that's the only way to figure this stuff out, right? I mean, this is an argument people have about electric cars. They say, oh well, then we're going to have all these electric cars and we still have to make the power with coal or oil, and it's like, no, the idea is we transition the grid to renewables and then we power the electric grid. But yeah, so it's the same idea. If you can get more information about where that fuel comes from and whether or not they're doing things like water and energy cataloging of the demand to produce the fuel, that's how to figure it out. But I don't know off the top of my head. I haven't zeroed in on United's sustainability plan.
Joe, we have a question here. in the room?
Let's take one question from the room and we'll need,
What
excuse me,
is
1
your
minute. 1 minute, please.
comment
1 minute,
on
please.
DOERR, who is just a Rice University graduate, he and his wife from Rice, had just funded $1.6 billion to create a new climate change school at the University of Stanford.
I can tell you that there were a lot of meetings amongst the Rice administrators on that day.
Well, he also had given the largest check to Rice University, $50 million at one limb to teach leadership at Rice.
Yeah, the Leadership Institute. Yeah, my comment is that I think a lot of us, I'll give a very diplomatic answer. A lot of the faculty at Rice are working hard to build capacity for Rice to be a leader in climate and environmental change. Stanford has done the work over many decades to become a leader in that space, and they got that money because they're ready to hit the ground running and use it to solve problems. Rice needs to make strategic hires and make commitments to be ready to lead in things like energy transition and climate change research and climate impacts and adaptation. And we're getting there, and the faculty are ready, right? There's 150 faculty at Rice who identify as environmental scholars. And we've been working for the last 5 years to try to get an environmental institute ready to go. And I think it's going to happen soon. I don't know whether or not the doors will be part of it. I would like to hope that they would see us as.
Both he and his wife are graduates of the electrical engineering school at Rice University.
I know a lot about them.
Okay.
All right.
This is way above my pay grade. I'm a lowly assistant professor,
Yeah.
but I think our development officers and our administrators are very much looking towards big investments in climate and energy transition for Rice
Great.
right now.
And with that, I know Joe wants to limit questions.
Yeah,
so I'm gonna
we've
swing back.
run past our time, unfortunately. Dr. Dee, I really want to thank you again. This was really awesome. And thank you to everybody asking these wonderful questions. Before everybody drops off, I'd like everyone to turn on their cameras so we can take a nice group photo. And then after that, we'll continue on with our meeting, and everybody's welcome to stay or drop off if you need to. But if we could, please, everyone turn on your cameras. Still waiting for a few more.
I think they might be on phones.
Okay, I guess we'll do with what we can here. All right, everybody smile, please. And let me just double check to make sure that came out okay for us. Oh, very nice picture.
And we
Okay.
clapped. Sylvia, that was an excellent presentation.
Thank you.
Yeah, thank you.
Okay, Dory, can you make me a co-host again? Because I had lost my access, I believe.
Did you make?
I'm the
Emma-
host, actually.
Yes.
The Emerson computer is a co-host. You can just add me as a co-host.
I will do that.
Joe, she said that we could get some of the slides and stuff, the materials that she's got. I'd love to have that so that I
Yeah.
can.
Yeah,
So if you can gather
Dr.
that up.
Dr. D, we'd love to get that from you. If you can just drop us an email with all that information and photos.
Yeah, it's no problem. Or you can email me.
Excellent. Okay,
Joe, I do not appear to be able to make you anything.
I'm good now.
made you
I'm good. I'm gonna start sharing now.
No problem.
What can you say for the rest of you?
I can answer.
Hey, Jenny, David.
Can everybody see our screen?
Who? Yes.
You mentioned that name.
Hey, Dory, I'm hearing a lot of background noise from the room. We're continuing with our meeting now. Okay, so at this point, we're going to continue, Mark, with our monthly calling campaign. And let me get to that slide.
Joe, could you back up your first page? I think we've got a couple of new attendees.
Well, we've run out of time, Hans. I apologize, but we're going to have to continue
right.
on here.
Okay.
So we're in the section now where we'll do our monthly calling campaign. And Mark, if you can lead us through that.
Sure. Welcome, everybody. So there's the link. If you don't have the representatives for your district's number, and the good thing about that link is when you log into that, they give you a little short paragraphs to say, so you don't have to wing it when you're calling your representative. And it does change depending on whether your representative is a Democrat or a Republican. So I think the next slide also has some local numbers. Usually those are easier to access. They don't fill up the voicemail as quickly. So if everybody wants to get out your cell phone, if you have it available, and go to that link and get your rep's number, or you can pull it off of this if you know who your rep is.
And here in the room, we have different, you can just walk down the hall and pick a different room to make a call.
Yeah, kind of disperse. So I'll do.
Okay. So yeah, after Mark does his demonstration, then we'll pause here for 5 minutes. And then after 5 minutes, we'll resume with the meeting. If you're not able to make all your calls within that time, we ask that you do those offline after the meeting concludes. Go ahead, Mark.
Okay, I'm calling my representative. Hello, Representative Hunt. My name is Mark Harrinan. I live in zip code 77080. And I'm asking you to help our country win. Take a look at the carbon border adjustments that give the US manufacturers an advantage in the global marketplace. Example would be HR 4534, Fair Transit and Competition Act. Thanks for your consideration of this. I'm going to call my senators too.
It looks like everybody more or less has finished making their calls. I've put the in-person meeting on mute because they were making a lot of noise while we were calling. I'm going to go ahead and continue with our meeting agenda, and I'm going to share my screen again, and we'll get into the slide deck. Dory, I'm not sure if you're able to hear me. I did put you guys on mute, but I'm going to continue with the meeting now. All right, so continuing on, some more Citizens Climate Lobby news information. That's good information. If you can see my screen, here is a CCL legislative update from from Flannery Winchester, our CCL Senior Director of Communications. And this is in regard to permitting reform in Congress. And permitting reform is one of our key objectives for this year and is very, very important. I'm going to play that video now.
Hello CCL, I'm Flannery Winchester, your Senior Director of Communications, coming to you today with an update about what's going on in Congress with permitting reform and what you can do to help. As you know, permitting reform is one of CCL's 4 major policy areas that we're working on, and we're working on it because America needs to build and connect a whole lot of clean energy fast, but slow permitting processes are causing a bottleneck. Basically, the clean energy revolution is ready. We just need to cut some red tape. So here's what's going on. For the last few weeks, there have been rumblings on Capitol Hill around permitting, with signals of more to come. At the end of February, E&E News reported that House Republicans were working on multiple bills that would ultimately be part of a sweeping energy and permitting reform package that would come to the floor at the end of March. There have already been a few hearings in different House committees to start to explore those initial bills. The Biden administration has been talking about this too. At an event earlier this month, White House Energy Advisor John Podesta said permitting reform was high on the administration's agenda. He said that the permitting process for clean energy infrastructure is, quote, plagued by delays and bottlenecks. And he said there's plenty that we can do and must do federally. And again, what we can do is update those permitting processes in a way that preserves community input while letting us build and connect a lot of clean energy fast. So the latest is that on Wednesday of last week, House Republicans dropped their big energy and permitting reform package, which they're calling the Lower Energy Costs Act. They gave it bill number HR 1. And Speaker of the House, California Republican Kevin McCarthy, said in a video, "We can streamline permitting and still protect the environment. That's a goal worthy of the number 1." So that's great to see and to hear. Now, as with any major policy, the first version is not what's going to get across the finish line. Our legislative team and others in DC are thinking of this package as just the opening bid in the permitting discussion. Ultimately, any permitting reform legislation will need to make it out of the Republican-controlled House through the Democratic-controlled Senate and to the president's desk for a signature. So there's going to have to be a bipartisan negotiation to make that happen. And that's where Citizens Climate Lobby volunteers come in. Who better to foster bipartisan discussion on climate policy than all of you? Seriously. Because of the way we have always approached our citizen lobbying, which is by meeting with nearly every member of Congress on both sides of the aisle year after year, we are uniquely positioned to encourage that bipartisan cooperation that's needed on permitting reform. And Congress needs to hear from the grassroots on this so they don't let this moment pass. When a transmission line takes 10 years, it's hard to have clean electricity by 2030. So now's the moment, and we need to urge Congress forward. So we've got our Conservative Climate Leadership Conference coming up next week, where we'll have a bunch of our conservative volunteers on Capitol Hill meeting with Republican offices about this very topic. And then in June, we have our annual conference and our big lobby day, again on Capitol Hill, with hundreds of volunteers from all over the country. Registration is open for that now, so you can see the event details and plan to join us. And we need you there so that you can help us take this message to Congress. We need to tell them clean energy is ready to go. Now we need to deploy it. Updating these permitting processes could save the planet. So thanks for all you're doing, CCL. Join us in June, and let's keep going.
All right. So I hope that was good information for everybody. I thought that was a really wonderful video that Flannery put together. Roger, I can't see if you're still here. Did you want to talk about the upcoming cocktails and conversations?
Sure, I'll just keep it real short. In 2 weeks, we're going to have the next cocktails and conversations. If you don't know anything about green ammonia, and then you're probably then like me, former CCL Houston member, and I think he was the chapter lead as well as our Third Coast regional coordinator, Peter Bryn, has started a new company. He's a project development officer of Eolic Green Ammonia, and they're looking to put in a 1 million ton per annum green ammonia facility in Texas. And he's going to kind of go through the basics and describe what he's doing. So I think it's going to be a really good episode, 4 o'clock in 2 weeks from today.
Thank you, Roger. I'm going to go on. We have one more really nice video, which is pretty short. It's less than 2 minutes from our executive director, Madeline Para. I just want to play this because I think this is good for everybody to watch as well.
We've experienced yet another year of historic climate disasters. Meanwhile, politics are as polarized and dysfunctional as we've ever seen. And too often, political engagement stops at the ballot box. At Citizens Climate, we're changing that. Since 2007, we've been advancing impactful climate solutions by helping citizens engage with our country's highest offices.
Whether you're on the reservation or from a small town or state, you can write a letter or call and talk directly to congressperson themselves.
And Citizens Climate's respectful, unifying approach bridges America's deepest divides.
I have been a conservative all my life, yet today I work with people who are very progressive. We all understand and are fighting for the same goal.
We take everyday people, artists, teachers, pastors, students, veterans, and turn them into effective citizen lobbyists.
Citizens who pass laws, who help a conservative state to become a climate leader, who gain access to democracy's inner circle, and who transition from coal mining to climate action. Citizens whose voices really do make a difference.
So I thought that was great. I wanted to share that with everybody. Next here, Larry, are you still on? Larry Howe?
Yeah, I'm here. Hi.
Hey, Larry, we have these slides that Susan Adams had shared with us. Do you want to just talk about this real briefly? We don't have a lot of time, but I want everyone to be aware of this.
Yeah, first a big thank you to all the people who've were able to make the trip to Austin for a couple of days. And we ended up having about 81 people from all across the state, as far away as El Paso, but also Lubbock, North Texas, Austin, Houston, San Antonio, kind of a wide range. I think even maybe somebody from the Brownsville area. And we covered 25 out of 31 Senate districts and 41 State House districts. Those are smaller, there's 150 of those. And we had 66 meetings scheduled that took place. 47 of those were with Republican offices, 19 with Democratic offices. So effectively, we covered about a third of all the legislative offices. And then we also had volunteers that have leave behinds to all the different offices that we didn't have direct visits with. So overall, it was an opportunity to kind of introduce Citizens Climate Lobby to our state elected officials. Again, we think of this as grass tops influencers for our members of Congress. So if we can get more of our state legislators aware of this issue and being willing to talk about it, it helps us in our conversations with our members of Congress. I did put a link in the chat just a few minutes ago. We're trying to get as many people as possible in Texas to join this community group that we have set up in CCL community, where we have some information that we used in planning and holding those meetings, those lobby meetings and training. And then we're also going to use that as an outreach for other actions throughout the rest of this legislative session. But even more importantly, as we go in between the sessions, it's opportunities to continue and grow those connections with those legislative offices as longer term grass top influencers. So Susan Adams had sent out a survey, and so far I think all the results have come back pretty positive, some good suggestions, but most people that attended said, hey, we're ready to do it again in 2 years.
Excellent. Thank you, Larry.
Mm-hmm. Thanks for the opportunity. Yep.
You're welcome. I'm going to skip over a couple of slides here. This slide here is just another reminder for everyone that we do need more help with our lobbying teams. And as we mentioned earlier, we have that June National Conference meeting coming up in Washington, D.C. We really want to send as many as we can, and we need folks to be able to volunteer to help out with that. So if anyone is interested and you're not already involved, Judith Hyatt, her email there is there, or just put something in the chat so we can see it and we can get back to you. We have our Earth Day celebration coming up, and we'll have a tabling event and a big tent.
Joe?
Yes.
I know we have no time. Judith would like to say a word back on the previous slide.
I'm at Emerson.
But you have to unmute us, Joe.
I can hear you speaking. Go ahead.
I would just like to say that if anybody is going to Washington, can you shoot me an email so I can organize the online meetings, lobby meetings that won't be in Washington?
Okay, so email Judith.
Okay, Judith, anything else? We're out of time here.
No, that's fine.
Thank you. We have our Earth Day event Saturday, April 22nd, starting at 12 noon through 5. And we'd love to see everybody come out and see us out there at the Discovery Green. So that's an annual event we always do. It's a big event for us. Here's the info on the June Lobby Day event in Washington, D.C. Registration is open. And I think for today, we're going to skip over our normal lever status meetings. We're just out of time. We'll stop here. I'm going to stop sharing. Any last questions from anybody or any other feedback on anything? And I really just want to thank everybody for joining us.
Great meeting, Joe.
Thank you. And thank you again, Dr. Dee.
Thanks, Joe.
Thanks for having me.
Have a great weekend, everybody. We'll end our meeting here.